Hi, my name is Tareem, and today my presentation topic is Hybrid Off-Grid Renewable Energy System for Remote Communities, a case study of Bella Coola, British Columbia with micro hydro integration. We mainly divided the presentation into three main topics. First one is introduction, second one is system modeling and main contribution, and third one is conclusion and future work. Let's start with the introduction. Addressing the remote community energy challenge in Bella Coola requires a sustainable and reliable solution. Relying on diesel is very costly and also cause a lot of environmental problems. To overcome these challenges, we propose a hybrid renewable energy system that combines solar, wind, microhydro, battery storage. Our goal is to minimize fuel consumption. This would give the community reliable energy, save money, and be better for the planet. Hybrid renewable energy system, a path to sustainable energy. As the world shifts towards sustainable energy, hybrid renewable energy systems offer a promising solution for remote communities like Bella Coola. By combining all these energies with storage, we can improve energy reliability, reduce cost, and minimize environmental impact. Our study aims to explore a diversified hybrid system that maximizes energy reliability and minimizes diesel usage, the way for a more sustainable energy future.
Okay, so let me do the part two and part three. So part two is system modeling and main contributions. So designing an optimal hybrid renewable energy system for Balakola requires careful integration of climate data, energy resource characteristics, and community demand profiles. Renewable resource data were collected from NASA Surface, Meteorology and the Environment Canada database. Monthly average values for wind speed at 50 meters height, solar insolation, and river discharge were analyzed to determine seasonal availability of energy sources. The stream flow rate data reveals a significant seasonal variation in hydro resource availability, with peak flows occurring during the snowmelt period from May to July, and lowest level observed in winter. These trends imply that hydro generation can serve as a baseload source during spring and summer, while battery or diesel support may be required in winter to maintain system reliability. The load profile for Bella Coola was derived based on typical residential and community scale usage in off-grid indigenous and remote Canadian communities. A daily average electricity demand of nearly 21,000 kilowatts per day was assumed, with a peak load reaching 1.32 milliwatt during winter months due to the heating and lighting requirements. So for this page, it shows that what we have done in this project. 6 hybrid system configurations were modeled using Home Pro. Each included varying combinations of the following components: the PV, the wind turbine, microhydro, small hydro device, battery energy storage, diesel generators, and it shows that 6 models, various configurations. Also, we do the sensitivity analysis. The diesel fuel price increased, the river flow reduction to simulate the dry years, Table 1 also shows the summary of several hydropower turbine parameters. Like all hydro systems are assigned a 30-year lifetime, consistent with mechanical expectations for hydroelectric infrastructure. Turbines were selected to reflect Bellacola's topography and hydrology, favoring low head, high flow designs, which are typical of coastal mountainous river. So this is our main contributions part. The first contribution is this table. Like the Homer Pro simulation yield key performance indicators, including LCOE, renewable energy fraction, diesel generator runtime, and excess electricity production. So this is the summary of result. Like Model 1 achieved 100% renewable fraction, but suffered from very high excess and electricity, and LCOE is too high due to the lack of dispatchable and baseload sources. Or like Model 6, which use a larger hydro unit, improved renewable fraction to more than 90%, but incurred higher excess generation and system complexity. So these results demonstrate that microhydro integration significantly reduced diesel usage and cost, while also improving load matching. The second contribution is about sensitivity analysis, like the river flow reduction 20%, which to represented dry years caused a significant increase in diesel usage and operational cost. Also for the analysis 2 is about diesel fuel price. When the diesel price increased from 1.2 to 2 per liter, the net present cost rose from 30.5 million to 35.2 million, increase of 15.4%, and LCOE increased. The annual cost also increased from 1.16 to 1.49 million. And part 3 is conclusion and future work part. For the conclusion, this study presented a comprehensive design and techno-economic evaluation for hybrid off-grid renewable energy system tailored for Bella, a remote coastal community in British Columbia, by modeling 6 different system configurations in Homer Pro, featuring various combinations of PV, wind turbine, microhydropower, diesel generator, and battery storage. The research aimed to identify a configuration that minimized fossil fuel reliance, lowered the LCOE, and enhanced year-round reliability. Among all 6 configurations studied, Model 4, which integrate PV, wind, medium-scale, microhydro, diesel backup, and battery energy storage, demonstrated the most favorable balance. The LCOE of this system is about 0.308 kilowatt, and the diesel generator has reduced to 17.2, and the renewable fraction achieves 77.7%. Meanwhile, the excess energy has kept moderate. Also, the sensitive analysis further emphasized the importance of robust design against environmental and economic uncertainties. Like a 20% reduction in hydro flow caused a significant increase in diesel usage and operational cost. Or the diesel price increase underlying the vulnerability of hybrid system to fuel price volatility. So this finding reinforced that microhydro integration is not only technically suitable for Bellacola's landscape, but also economically impactful. It enables higher renewable penetration and offsets diesel dependence, particularly when paired with intelligent seasonal dispatch strategies and energy storage, accurate energy storage. So for the future work, like a resource load mismatch, Bellacola's river flow peaks in late spring and summer, probably due to the snow melt. However, load profiles indicate that peak energy demand occurs in winter, primarily due to heating needs. That will cause two situations. When the hydro output is high, while load is low, this will increase the excess electricity. When the hydro output is low, while load is high, the system will have a greater reliance on diesel or battery storage. Meanwhile, batteries can particularly buffer this mismatch, but may not fully eliminate diesel need. So in winter, a rule-based dispatch where batteries serve mid-peak and diesel fills deep gaps is necessary. So the picture below shows that this kind of dispatch. Also for the future work, a control model in Simulink will be developed to simulate real-time energy management strategies, particularly focusing on hydro-diesel battery coordination and their seasonal constraints. This addition is expected to enhance the system dynamic performance evaluation and provide a more realistic control framework for future implementation. So thanks for listening. That is all.